So hi everyone. In this video, we are going to calculate the genus of the two floors, the function field that we obtained at the top of the two floors that we just talked about in the previous video. Right, so recall that we're looking at this function field, f2, and we're join x, y, and z, satisfying y squared equal x cubed minus x, and same for z and y. And we already found the rational places of this function field and so forth, and we ended up kind of summarizing those rational places that we found using this kind of diagram that we talked about. Okay, now in order to compute the genus of this function field, we will need heavy tools that we'll talk about, and these are the Horowitz genus formula and Dedekind different theorem. So what is the Horowitz genus formula? So it tells you that if you have a function field extension, f over L over E over K, and as usual, we're going to assume finiteness and separability. And you know, again, I'll remind you again what exactly separability means and so forth for the rest of the course, but you know, trust me that all of the function field that we are considering are splitting fields, so they are of separable polynomials, so these are separable extensions. And anyhow, let's assume that the genus of the lower function field is denoted by GE, and of the higher function field is G sub F. So these are the genera. So it turns out that the relation between them is as follows. So you have that twice the genus of the larger function field minus 2 is obtained by taking the same expression for the lower genus, and you multiply it by the ratio of the function field extension indices, f over E and L over K, and usually L over K is 1. In our case, it's going to be 1. So you only see f over E, the degree extension. But then you have to add the degree of a certain divisor, which is called the different. An important divisor in function field extension is called the different, denoted like that. Now, so kind of all the magic appears here, because I mean, assuming that you know GE and kind of you do by recursion or something, you already know the previous one. And of course, you know FE, this index, and usually K is L. So really the question is, what is the degree of this different? Now, I can't even define the different yet because it requires some work. But anyhow, what we can say is that you can write this different as follows. You can write it. So it's, you know, generally speaking, it's a divisor of the larger function field. So you can always write it according to, you know, first of all, you write all prime divisors in the lower function field, and then for each of them, you sum up all the extensions of them to prime divisors above them. And you have this prime divisor appearing here, and the number that appears as a coefficient in this different divisor. So that number, I mean, I want to define it. I want to kind of show that this is a divisor, namely there are only finitely many such numbers that are non-zero. But you know, generally speaking, I cannot do it yet. But what we will be able to do is to state another, again, a big hammer that we'll talk about, which is called Dedekind's different theorem, which relates this number with the familiar ramification index. Okay, this in some cases. So what is this Dedekind different theorem that will kind of demystify the different divisor? So again, we are in the same setting. F over L is a finite separable extension of E over K, and you take a prime divisor at the lower level and a prime divisor above it, capital P. Then the first thing you always have is that this mysterious D, it's called differential exponent, but never run. This D is always at least the ramification index minus 1. In particular, when you ramify, when a place P, capital P over small p ramify, it contributes the prime divisor capital P appears in the different. But moreover, you get equality if and only if the characteristic of the field, like F5 in our case, it's 5, the constant field, and all the characteristics will be the same, is not divisible, doesn't divide the ramification index. So once the characteristic doesn't kind of cause trouble and it doesn't divide the ramification index, you get equalities. And when you get equalities, you really completely understand what is the different divisor. This is precisely, it kind of encodes all prime divisors in the upper function field that ramify. And the multiplicity in which they appear is this ramification index -1. So in our case, that will be the case because the characteristic is 5 and the degree extension is 2. So in the ramification index is either 1 or 2. In any case, it's too small for 5 to divide it. So the Dedekind different theorem tells us that the different is precisely, again, as I said, the divisor that encodes all the prime divisor capital P that ramifies over the smaller function field, and the multiplicity is this number. In particular, as a corollary from that, you know that, as I said before, so the different exponent, this D is 0 exactly when you don't ramify. And because this is a divisor, that's a theorem. Because the different divisor is a divisor, it means that only finitely many capital P's actually ramify, or also small p's, ramifying the extension. Right, so this is something we didn't know so far. Could have been the case that there are infinitely many places that ramify, and it turns out the answer is no. And you could have asked, who cares about ramified places? But then if you look at the genus formula, you see that you want to understand which places ramify because they affect the genus, how it changes from the previous flow to the current flow. So we're going to talk about Dedekind's different theorem and Hurwitz genus formula later on in the course. Mostly, we're going to talk about it in the physical lecture, but most of the proofs are going to be on videos because they are somewhat complicated and we kind of run out of time. But let's take these two as granted. Okay, so we know the Hurwitz genus formula. And we know the Dedekind different theorem. And it tells us that if you want to compute the genus, you just have to figure out what are those prime divisors that ramify. Okay, so let's do that. So by Hurwitz genus formula, and since the genus of F1 is 1, we know that so twice the genus that we're looking for, -2, is twice the older genus -2 plus the degree of the different, and G1 is 1, so that actually completely goes away. And moving things around, we get the G2 is 1 plus half the degree of the different. And as I said, in our case, the different, which you usually write like that, the characteristic is 5, it doesn't divide 1 or 2. That's called a tame extension, by the way. We'll talk about it, but tame means that the characteristic doesn't divide the ramifications, which is in our case true. So these D's can be replaced by the ramification index -1. So really our task is just to find all ramified places and therefore we can compute this difference or the degree of. And actually we found already 6 places that ramify, right? In this extension. In this extension, sorry, F2 over F1. Right, so these 6. This is a previous calculation that we did. And so this already mean that the genus is at least 4 or something, right? Because the degree of the difference is what matters for us, and for computing the genus, we should divide it by 2 and add 1, and multiply the degrees of the prime divisors that appear in the different, because I'm computing the degree of the different, which is this sum, but with replacing Q with the degree of Q. And all of these places are rational, so they have degree 1, and there are 6 of them. So G2 is at least 1 plus a half times the degree of the difference, and the degree of difference is 6, or at least 6. Right, so actually this is an equality, and now the fact that this is at least 6 is because potentially there could be other ramified places, but then this is at least 4. So the genus is at least 4 because we found 6 ramified places, and potentially it could be 4, but actually it turns out that there are other ramified places which are not over rational, do not correspond to rational prime divisors, right? So these are all the prime divisors that you have in F2, and for coding theory, for example, you only care about rational places in order to decide at what prime divisors you're going to evaluate. But because you also care about the genus, and the genus is affected by ramification, you also care about non-rational places. You care about all places that ramify. So we are going to kind of be in the pursuit of trying to figure out what are the other prime divisors that ramify, even though they are not going to be over rational places, because these are the only rational places in F1, and these are the only rational places in F2. So in order to do that, to find the other ramified places, we are going to take a little detour and compute the principal divisors of X, Y, and Z in F2. That will help us doing that. Okay, so let's continue. So we already know what is the principal divisor of X in F1. That's just, we did it before. It's 2p00 minus 2p infinity, and it has a 0 at p00 with multiplicity 2, and a pole at p infinity, capital P infinity, of course, in multiplicity 2 as well. And so this means that the principal divisor of X as an element in F2 is this thing, right? So I mean, we just kind of, because Q000 is the only place above P00, and the ramification is 2. So this means that the valuation of X as an element in F2 is twice as much as it was before, and same for the polar. And similarly for Y, right? We know that the principal divisor of Y in F1 is this thing. We already talked about that. So these are its 3 distinct zeros, and it has a pole of order 3, infinity. And therefore, as an element in F2, Y is going to have kind of, for each of the prime divisor line above those, it's going to have a coefficient multiplied by the ramification. So, and the ramification was always 2, so everything is multiplied by 2. And the question is, what can we say about Z? So what's the principal divisor of Z? That's kind of more complicated, because in X and Y lived as functions also in the previous function field, so we only had to multiply by the ramification index, but Z is a new function. It never appeared in F1, so it's always slightly harder to figure it out. Yeah, and in this case, actually a bit tricky. So we want to ask, what are the prime divisors that are poles and zeros of Z? So we want to kind of focus our search. So what we are going to do is to say, well, if Q is some pole or zero of Z, then of course that happens by definition. And I want to kind of relate it to Y, so I'm going to say, well, this is equivalent to that, because VQ of Z squared is twice VQ of Z. And now, because Z squared is Y cubed minus Y, I can say that, well, if there is a prime divisor Q such that VQ of Z squared is non-zero, then it means that the prime divisor capital P below it also satisfies that, because only the ramification index will be the ratio between them. And because I'm now in F1, I'm looking at capital P and not at a Q, I can replace Z squared by Y cubed minus Y, because it's the same function. So, right, so what I'm saying is that any kind of suspect Q for a pole as a prime divisor suspect of being a pole or a zero of Z, it has to lie over a capital P, which is something that we better understand, for which this holds. Okay. So now let's consider two cases. So first of all, let's assume that V capital P of Y is non-zero. Okay, so under this assumption, we know that VP of Y cubed is not the same as VP of Y, because it's 3 times VP of Y, and VP of Y is not 0. So, right, 3 times a number, it's not a number if it's not 0. So this means that also the valuation of Y cubed minus Y is not 0, because according to the strict triangle inequality, it's either the valuation of Y or 3 times the valuation of Y, depending on whether or not it's negative or positive. But anyhow, it's definitely non-zero. So this means that for every pole and zero of y, you get a pole and zero, pole or zero of y cubed minus y. And these, as we said here, give you poles and zeros of z. Right? So because we know that the principal divisor of y over f2 is this thing, then you immediately get zeros and poles of z. Not all of them, maybe, because I'm kind of under this assumption, but not all of them, but some of them. Right? So we know that the principal divisor of z also corresponds to this, to these prime divisors. Of course, the coefficients would be different. I mean, I never said that VQ of z equals V, whatever, but you can figure out the coefficients just by computing the valuations. So the principal divisor of z is Q00. See, the 2 here is a 1 here actually, and Q100 and Q minus 100 here. And actually, this minus 9 you already showed them before, but never mind. And then Q infinity appears with a multiplicity 9. But of course, there is also the other case, namely, I mean, we know that the poles and zeros of z are above, lying over poles and zeros of y cubed minus y. And under the assumption that v capital P of y is not 0, we found some places. But now we have to consider the other case. And this will give us the rest of the poles and zero of z that we missed out. But actually, before doing that, let's just take a detour just to explain the point. We just saw that z has right, so I'm just copying this thing here. So z has this as a zeros, this as a pole, and then there should be other stuff coming around. But I claim that you already know that this 9 is I mean, there are no more poles, right? And the remaining 0 should have a total degree of 6 to make sure that this is 0, the degree is 0. And the reason is, if you remember, at some point in the course we proved that the degree of the pole divisor of z in this case, as I name it in F2, is exactly the extension of F2 over F5 of z. Generally speaking, the degree of the pole divisor of an element is always the function field, the index of the function field over the rational function field when you adjoin that element to the constants. And okay, so what is F2 over F5 of z? Well, F2 is just this thing with the underlying algebraic relations between x, y, and z. And let's break this down according to, in between by looking at F5 of y and z. Now, we know that, I mean, it's easy to verify that z squared equals y cubed minus y, or z squared minus y cubed plus y is irreducible. It's actually the minimal polynomial of z. So it's the minimal polynomial of y over F5 of z, right? And so this thing has degree 3. Right? When you adjoin y to z, then the irreducible polynomial is y cubed minus y minus z squared. It is going to be irreducible, so the extension here is 3. And for the same reason, the extension here is 3, the degree of the extension, right? Because when you add x to those, well, you need to show that also xu minus x minus y squared is irreducible, but it is. And so all in all, what happens is that this degree extension is 3 times 3, which is 9, which explains the 9 that you see here. Okay, and it tells you that you're not going to see any more poles, you're only going to see zeros, and the degree of these zeros, like altogether, is going to be 6, because the degree of each of them is 3, and you have a minus 9 here, everything here is a rational place. So you need either 6 more rational places, which probably they're not going to end up only with rational places, or maybe some lower number of non-rational places. And we are going to get a mix of both. Okay, so let's see. So again, we're in pursuit of finding the other prime divisors in the principal that appear in the principal divisor of z, and we're in case 2. Namely, now I'm assuming that I'm looking for capital P's. I mean, I'm looking at Q's, but underlying them are capital P's for which v capital P of y is 0. Okay. So what do we know? We know that VP of y cubed minus y is VP of y squared minus 1 plus VP of y. That's the usual thing. And VP of y is 0, so that's why I wrote it like that. I can factor the y. So I know that the valuation of this is the valuation of that. And we like y squared because y squared is equal to x cubed minus x. So if q, right, we're looking for a q, we're searching for q's, but now we're kind of looking at a p, capital P that underlies this q. So if little p lies under capital P, and the valuation is non-zero, like we're assuming the valuation here is non-zero, right? Not of y, of this thing. The valuation of y is 0. So if the valuation of this is non-zero, which is the same as saying the valuation of this is non-zero because this is 0, then for, at the lowest level, small p, the place small p that lies that underlies, sorry, capital P, we get that v small p of x cubed minus x, which is y squared, minus 1 is also non-zero. Right, so what I'm saying is that this q that we are looking for, a 0 or a pole of z in F2, we said, well, it lies above capital P, which we are kind of searching for. And then we just said that, well, it has to lie, capital P has to lie above a small p such that this holds. Right? That's the only places we have to look at. And actually, we already kind of encountered this expression. So x cubed minus x minus 1, you can factor like that. And so what we figured out is that the only small piece downstairs, above which, like in 2 levels above, z may have a 0 pole, are exactly P2, corresponding to this factor, and P of that polynomial, that irreducible polynomial. Right? Recall that in the rational function field, you have a place or prime divisor for every irreducible polynomial. And these two are irreducible polynomials over F5. Good. And actually, we already showed that there are 2 prime divisors. I said I will leave you to show, but actually, I already did that. There are 2 prime divisors of F2 that lie over P2. Let me show you the picture that we had. Right, so this is P2. And these are the 2 prime divisors. I mean, these are the local parameters of them, but these points are the 2 prime divisors that sit above P2. And they, right, so there's that. And what's not drawn here are the new prime divisor at the bottom, which corresponds to a degree 2 irreducible polynomial. Right, so we already found we already found 2 more zeros corresponding to those things in P2. Maybe I have it here. So these are these two. Right, Q2, that's the name for them, Q2 10 and Q2 minus 10. And now as for the more intriguing prime divisor, this prime divisor, so let's denote it by P prime because it's kind of long. So what do we know? So we know that y squared minus 1 is x cubed minus x minus 1, which is factors like that. I'm shooting for using Kummer's theorem, so I'm trying to go somewhere here. And so the minimal polynomial of y over f5 of x, which you usually write just as, y squared minus x cubed plus x or something, right? I want to write it in a way that kind of shows you this expression. So you can write this minimal polynomial, anyhow, by replacing x squared, x cubed minus x with minus 1 of this expression, you can write it as t squared minus this expression, which encodes this polynomial, minus 1. Right? That's just a weird name of writing x cubed minus x. So that's the minimal polynomial, but the reason I write it like that so that you can see that, well, it's a harmonic polynomial, and the coefficients are in the valuation ring corresponding to this prime divisor. Namely, essentially what I'm saying is that this polynomial doesn't have a factor of that polynomial appearing in the denominator. Actually, it has a factor of it appear in the numerator, but then there is the +1 or -1, right? But you know, so I'm just writing it like that so that you can see that we're in the position to apply Kummer's theorem. And Kummer, because y is in OP prime prime, and Kummer's theorem tells you that you should just project that polynomial to that prime divisor, namely this thing is 0. And when you do that, you get this polynomial, t squared -1. Okay? And Kummer's theorem tells us, well, if you get t squared -1, it's a t plus 1, t minus 1. So there are two prime divisors lying above this prime divisor in F1 over F0. And per our usual notation, we write the first coordinate, but now it's not a coordinate, it's a rational, it's a polynomial, but you know, it's on the x minus 5, it's this polynomial, so I can't replace it by 5. I can just write the name of the polynomial. Or if you want, I can write it, you know, x minus a solution, you know, one of the roots of that polynomial, and then its conjugate will be implied. But anyhow, you just write it like that, with a 1 and with a -1 corresponding to the t plus 1 and t minus 1 factors that you have. Good, so that's the picture. So I mean, okay, so before the picture, that's the principal divisor of Z. You had the easier prime divisors to find, and then you had these two that kind of were slightly hidden, but there were these two which were more hidden even more because they lie over non-rational prime divisors of X in like in F0. Right, so I'm talking about this thing. So this non-rational prime divisor in F0, above it you have two rational places, like not rational, two places. They are not rational anymore because I mean the degree of this prime divisor is F here, which is 1 times the degree of that, but the degree of that is 2. So this is a non-rational place, and also this one. And what I will leave you to show, but that's kind of the same of what we did all the time, is that above each of them, you have a totally ramified place. But you kind of know that because you know that once you have a 1 here, you will get a 0 afterwards, right? So that's what happens all the time with complete ramification. And also with -1s, you get a 0. Good, in terms of degrees, everything's fine, right? Because you have like 1, 2, 3, 4, 5. If you get a 6, like 9, 1, because you have this pole with multiplicity 9. So you have 1, 2, 3, 4, 5, and then 6, 7, 8, 9, because the degree of each of them is 2. So all's good. And here I wrote down the principal divisors. So for example, the principal divisor of X is very simple. You have 4 zeros at 0, or 0, 0, 0, 4 poles at infinity. Y has kind of more interesting behavior. It also has zeros at 1 and -1. And Z has like a kind of a weird 0 pole pattern. You have like 1, 1, 1. All the poles are at 9. And then you have 2 more zeros here and 2 non-rational zeros here. So with this, let's look at some Riemann-Roch spaces. You'll see in a second why we care about that in the context of computing the genus, but let's just do that. So from here, we see that the pole divisors of X, Y, and Z are just multiples of Q infinity, right? So in particular, X has 4 poles at Q infinity, Y has 6, and Z has 9. And with that, we can compute elements in the Riemann-Roch space of R times Q infinity for increasing values of R. So for example, so here I wrote the degrees, like R. Here I wrote the the Gill dimension. So that's the dimension that I was able to find. So I'm trying to populate a Riemann-Roch space, so I'm finding like independent functions there. Maybe not a basis. Maybe I didn't find a complete basis. It turns out I actually did. Potentially speaking, I mean, strictly speaking, I write here the dimension as I found it. And here are the functions themselves that you add up every time. So for example, for a degree 0 divisor, you always have dimension 1, right? And the corresponding function is 1, right? Like F5 spanned by the span of 1 is the Riemann-Roch space corresponding to the 0 divisor, 0 times Q infinity. Now at 1, 2, and 3, I couldn't find any other any function there, because only at 4 I kind of start to see things. And this is not going to be an accident. That's going to be real. I mean, there are no functions here, but so far I don't know that. So you see there are like these kind of gaps. These are called Weierstrass gaps, which tells you that you increase the degree, but you still don't see new elements in the Riemann-Roch spaces. But once you get to degree 4, you can use X, right? X lives in L, the Riemann-Roch space of R times Q infinity, because it has pole only at Q infinity with multiplicity 4. So now the dimension, like the Gill dimension, is 2, because you have 1 and X sitting inside L of 4 Q infinities. Potentially there could be more, maybe. At 5 I couldn't find anything, but at 6 you can use Y, right? Because you have this 6Y here. So the dimension increased to 3, right? So the gaps are here, 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 and here at this point. And then you can continue like that. So, in degree 7, I couldn't find anything. At degree 8, I could use X squared. You need to make sure that you don't use, when I write a function, I need to make sure it's not spanned by the previous one, but it doesn't. So at degree 9, I can use Z for the first time, and then I can use XY when I increase the degree to 10, because 4 plus 6 is 10. At 11, I couldn't find anything, and from here on, I could find anything you want. So in 12, I can use Y squared, 6 plus 6. At 13, I can use X times Z, right? 4 plus 9. 14, I can use 2 X's, which gives you an 8 plus Y, which gives you a 6, and so forth. Okay, so it's kind of nice to see that this kind of tells you where are the potential gaps that you have. And it's not just nice to see that, because it enables us to compute the genus. Because if you trust me, then it's actually easy to verify that you can continue kind of populating the Riemann-Roch spaces with a new function every time you increase R from this point onwards. Then by Riemann-Roch, we know that the genus must be at most 6, right? Because Riemann-Roch tells us that from some point on, turns out at this point in this case, you can always fill things up. So it means that the degree minus dimension is G minus 1. And because I know that, and I know that I can keep populating, and I see that the difference here is 5, then the genus is 6, or at most 6, because maybe I could have populated more things here that I didn't. So this gives you kind of an upper bound, because it could be the case that I missed someone, but this gives you an upper bound on the genus. The genus is at most 6. But on the other hand, we know that the genus is at least 6 because of what we just did, right? If you remember, just using the divisors, the ramifications that we knew above rational places, we figure out the genus is at least 4. But now we just found out 2 other places that are of degree 2 that also ramify. So each of them will add 2 to the degree of the degree of the different divisor, which result with a 6, right? So you have this 1 plus half times the degree. It's written here, right? So you have this expression sitting here, and we had 6 ramified places plus 2 ramified places of degree 2. This is 2 times degree 2. So this gives you a 10. So the degree of the difference is at least 10. Potentially there are more ramified places that I missed out, but turns out that there isn't, because we just found out the degree of the difference is at least 10. Multiplied by 1/2 is 5, plus 1 is 6. So the degree of the difference is, so the genus is at least 6, but not at most 6 for a different reason. And altogether, we know that the genus is precisely 6, and also that we haven't missed any other ramified tests. So that's how we computed the genus in this example. Yeah, so that's the picture that we had, the missing ramified places. Good. So next up, we are going to do more floors. We are going to see. Well, we're not going to compute the genus because it's kind of difficult, but we're going to lower bound the genus and compute the exact number of rational places. At least, I mean, do a sketch of it, and that will show us what kind of code do you get using our example when you do more and more towers. That's going to not work very well. So it turns out that this example is a terrible code, gives you a terrible code. But then you are going to look at a much better tower, which turns out to be optimal at the end of the day.